All right, in this video I'll be finishing the notes from section 5.1. So we left off on slide 17. We had just talked about the three methods for probabilities. There was the empirical method, the classical method, or what I call the theoretical method, and also the subjective method. In statistics, our main focus is going to be the empirical method. We talked about how that's based on experiments, or an experiment, real data. It's basically data that's been collected. So here it says the probability of an event is approximately, notice the word approximately, the number of times event E is observed divided by the number of repetitions of the experiment. All right, so I want to just, again, focus on this idea of approximately. Remember, when we collect data, what we're looking at is a sample. And so if we're not, especially when we're not looking at a population, which we normally aren't, each sample you could end up with some different results. Although they should be similar, that's what we call variability when we do this. And so let me just, I'm going to go ahead and put up my notes, and I added something here that I'll just mention. So when we find probabilities using the empirical approach, the result is approximate because different trials of the experiment lead to different outcomes and therefore different estimates of the probability. As we increase the number of trials of a probability experiment, our estimate becomes more accurate. Remember, we talked about the law of large numbers. So that's the basic idea here. So for example, surveys are probability experiments. Results differ for each example because different people are included in the sample. Again, we talked about variability. So the best thing we can do is just make sure that we include enough people in our experiment so that we're getting a pretty good estimate of the true probability. All right, so let's go ahead and move on to the next slide and look at an example. So it says, pass the pigs. Oops, let me move this just a little bit down. Pass the pigs is a Milton Bradley game in which pigs are used as dice. Points are earned based on the way the pigs land. There are 6 possible outcomes when one pig is tossed. A class of 52 students rolled pigs 3,939 times. The number of times each outcome occurred is recorded in the table. Find the empirical probability of each event. So this is like finding a relative frequency. So the first thing you're going to want to do here is add up the number of rolls. And we actually know it's 3,939. They did tell us that. But you can confirm when you add those up, that's what you get. All right, so let's continue, and I'm going to move on to the next slide to do that. And so now we have the probabilities of each. So for example, this first probability of 341 thousandths, you get by dividing 1344, which was the frequency, divided by 3,939, the total of all frequencies. And if you do that division, you do get this number here to 3 decimal places. So you'll notice the leaning Jowler occurred 8 thousandths of the time. So we could say the probability of a leaning Jowler based on our data here is equal to, now if you move that decimal, you could write it as a percent. It would be 0.08%. No, 0.8%. Right, 2 decimal places to the right, or 0.008, which we say is 8 thousandths. So basically the idea is if you roll the pig 1,000 times, you would expect to get 8 leaning jowlers. Because remember, this is the ratio 8 out of 1,000. So for every 1,000 rolls, you're expecting to get 8 leaning jowlers. All right, so that's how we can interpret this probability. Let's go ahead and move on to the next slide. So we talked about the classical method, which is based on counting methods, or the way I've said it in the past is it's based on a study of the possible outcomes. And the key to this is our outcomes are equally likely. So the classical method of computing probabilities requires equally likely outcomes. Like when you roll a die, you're expecting to get a 1, 2, 3, 4, or 5, or 6. Or I should say any one of those outcomes is just as likely as the other. So this means each outcome has the same probability of occurring as the other outcomes. So for example, when a fair dice is thrown, each of the 6 outcomes in the sample space, 1 through 6, has an equal chance of occurring. So we know, for example, the probability of getting a 6 is 1 in 6. Since there's 1 6 in our sample space out of a total of 6 possible outcomes, and I didn't write that as a decimal. Oh, let's see, I'll just go ahead and divide that real quick. So it's 0.167 if you round to 3 decimal places. Again, in this book, we're writing probabilities mostly as decimal numbers, and that's especially true when we're working with empirical probabilities, but they're also doing it when you do the classical method as well. Let's go ahead and move on to the next slide. So I need to make sure you know what colors we're dealing with here. This is green, this is red, this region here, and this one is blue. So if you're like with the classical method here, you can see that each of these 4 parts of the circle, can you picture the spinner here? Basically this is where it spins around, and you can see each of these sectors are the same amount of same percentage of the circle. Each one is 1/4 of the circle. So the probability of getting a 1, for example, is 1 in 4. So here, what would be the probability of getting red? By the way, this could be written as 2500ths. And so probability of getting red, well, half the circle is red, so you could write it as 1/2 or 5/10. So those are examples of the classical method. Let's look at another slide on the classical method. So based on counting methods, or we said a study of the possible outcomes, not an actual experiment, the classical method of computing probabilities we talked about requires equally likely outcomes. Okay, so here's our probability of event E occurring is the number of ways E can occur divided by the number of possible outcomes. The way I like to say it is the probability of E is the number of favorable outcomes divided by the total number of outcomes. So for example, when we spun the spinner in the previous slide, we said the probability of getting a 1 is 1 in 4. That's because there's one favorable outcome where we get a 1 out of 4 total possible outcomes. Okay, let's move on to the next slide. So the way our book is writing this, or another way they write it, the probability here is, so if S is the sample space of the experiment, then the classical method can be thought of as the following. Probability of E is, let's see, N of E over N of S, where N of E is the number of outcomes in event E, and N of S is the number of outcomes in the sample space. So this is another notation that you'll see. So this one here, I normally say the number of ways that E can occur. And again, the denominator is basically the total number of outcomes. So again, the way I like to write it is favorable outcomes divided by total outcomes. But this is the notation that you'll see in this book. All right, so let's look at another example in the classical method. So a pair of fair dice is rolled. Compute the probability of rolling a 7 when the die are added. So this is actually part of a game, what is it, craps in gambling games. But you can see we have a 7 here. In fact, in each row we have a 7, and they actually form a diagonal. So P of E, we said, is equal to N of E over N of S. So basically the number of favorable outcomes, or the number of outcomes where you're getting a 7, there are 7 or 6 of those, versus the total number of outcomes, the total sample space. Well, there's 36 if you notice. There's 6 in each row or each column, and there's 6 columns. So 6 out of 36, which reduces to 1 in 6. And let's see. Again, in decimal form, that would be 0.16, bunch of 6's repeated, rounding to 3 decimal places, 167 thousandths. Or if you rounded to 2 decimal places, it would be 1700ths. So it just depends on what they ask for. Let's go ahead and do another one of these. So a pair of fair dice is rolled. Compute the probability of rolling a 2. Well, there's only one 2. So we said it's N of E divided by S of E, basically the number of favorable outcomes, or how many, basically how many ways can you get 2? Well, there's only one, or there's only one number in that set E, and the total number of outcomes again is 36, so it's 1 in 36. And you can divide that and you get about 0.02 and then a bunch of 7's. And so if you round to 3 decimal places, it would be 28 thousandths. Obviously, you're more likely to roll a 7 than you are to roll a 2. All right, so let's move on to the next slide. So using the classical method, the probability of rolling a 7 is 167 thousandths. Now let's look at the empirical method. Suppose you roll a pair of dice 100 times. So notice you're doing something. You're basically performing an experiment. You do it 100 times and obtain 15 sevens. So from the empirical evidence, you would assign the probability of rolling a 7 as 15 out of 100, or 1500ths. We would expect that if we continue to roll the dice and recalculate the probability, the empirical probability will move closer to the classical probability. Again, this is another example of the law of large numbers. The more times we perform the experiment, the closer the probability will get to the actual probability. All right, let's move on to the next slide. So the subjective probability of an outcome is a probability obtained based on personal or professional judgment. When would someone use subjective probability? I believe we talked about this in class. Basically, financial advisors do this all the time. They look at a lot of trends and then they make decisions based not on just trends, but sometimes what their gut feeling is saying about things. Um, for example, another case would be like if an earthquake happens and somebody determines the probability of there being a tsunami. So there's a lot of research they can do to determine that. They can base their decisions on things that have happened in the past. But again, this is a more, it's not just based on exact data collected like with empirical probability. It's certainly not classical probability. It's not something that you can just look at the possible outcomes. So this would be a case where you'd use subjective probability. Why would we use subjective probability? Basically because we can't do an experiment. And we talked about when we would use it. It's basically in cases where, again, you can't really look at the possible outcomes. You can't just collect data directly and determine the probability. There's a lot more factors, and experience is a big part of determining a subjective probability. Subjective probability does not use an experiment or a counting method to find probability, but instead is an estimate based on expertise or experience. Okay, our main focus is going to be on empirical probabilities. And I guess we're done here. So the only thing left to do is I will make a video for homework problems 5 through 8. So if you have any problems with those homework problems, you can watch that video, or it's there as needed. All right. Whoops, I just hit the wrong one.